When people hear the term satellite internet, the first image that often comes to mind is a bulky dish sitting in the backyard, pointed at a single satellite fixed high above Earth. For decades, that's exactly how it worked. A geostationary satellite, parked 36,000 kilometers away in orbit, would send signals down to your dish. That satellite appeared to sit in the same spot in the sky, so your dish didn't have to move or track anything. But while that system worked fine for broadcasting TV, it struggled to deliver fast internet. Every time you clicked on a web page, your signal had to travel 36,000 kilometers up to the satellite, then 36,000 kilometers back down, and then repeat the same journey in reverse when the server responded. That round trip added up to more than 70,000 kilometers of distance. Even though signals move at the speed of light, the delay was noticeable, about half a second just in travel time. For video calls, online gaming, or anything requiring fast back and forth communication, this lag was painfully obvious. Starlink set out to change this by rewriting the playbook. Instead of relying on one or two satellites in distant geostationary orbit, Starlink uses a swarm of thousands of satellites flying much closer to Earth, just 550 kilometers up. That's about 65 times closer than traditional broadcast satellites. Because they're closer, the time it takes for signals to travel between the ground and space is drastically reduced. Latency drops from hundreds of milliseconds to just a few dozen milliseconds, fast enough to make Zoom calls smooth and gaming responsive. But this solution comes with a big challenge. Satellites this close to Earth are not stationary. They orbit the planet at about 27,000 kilometers per hour, whipping across the sky in just minutes. That means no single satellite stays in view for long. To keep you connected, your dish has to be smart enough to track satellites as they move and to hand off your connection seamlessly from one satellite to the next. So how does Starlink differ from broadcast satellites, the kind used for satellite TV? Broadcast satellites essentially beam signals one way from space to Earth. They don't need to track individual users, they just spread content over a wide region. Starlink is completely different because it's two-way communication. Your Dishy McFlatface isn't just receiving signals, it's transmitting data back up into space as well. This requires highly directional beams that can precisely point at moving satellites. Now let's answer an interesting question. Starlink dishes don't move at all, so how can they track satellites racing across the sky at 27,000 kilometers per hour? The secret lies in something called phased array antennas. Think of it like this. Imagine standing in a field with hundreds of friends. If everyone shouts randomly, it's just noise. But if everyone claps or sings in perfect rhythm, the sound waves combine into something louder, clearer, and more focused. You could even aim that sound in a particular direction. That's exactly what Dishy does. But instead of people, it's thousands of tiny antennas, each transmitting radio waves in perfect sync. Traditional satellite dishes form a beam by physically shaping metal, much like a flashlight reflector directs light. A phased array, by contrast, replaces the reflector with math and electronics. Each little antenna sends its own wave, and by adjusting the phase, the timing, of those waves, the dish makes them align in one chosen direction. Where they reinforce, the beam is strong. Where they cancel, the signal disappears. The result is a laser-like beam of radio energy that can be aimed anywhere in the sky, instantly, without a single moving part. They bend invisible beams toward a fast-moving satellite. This is where Starlink completely changes the game. Geostationary broadcast satellites are like giant spotlights fixed high above the Earth, covering entire continents with a broad but distant beam. Starlink, on the other hand, is like a swarm of spotlights sweeping across a stadium, with your dish electronically steering to lock onto the nearest one. The result is faster, sharper, and far more dynamic internet, but it also demands breathtaking coordination between thousands of satellites in orbit and millions of dishes on the ground. Now let's talk about the dish itself, because this is where the real magic happens. Dishy McFlatface isn't a curved reflector like traditional satellite dishes. It's a flat, layered sandwich of advanced RF and digital technology. At the top is the radome, a thin weatherproof cover that's transparent to microwaves and even has built-in heating to melt snow and ice. Beneath it sits the radiating layer, thousands of tiny copper patch antennas etched into precise patterns, designed to operate in Ku-band frequencies. These patches rest on a low-loss substrate like Rogers Row 400, supported by a copper ground plane that reflects energy upward. Just below lies the RF front end, with low-noise amplifiers to capture weak signals from space and power amplifiers to boost outgoing ones. Beam steering is handled by phase shifter chips that synchronize every antenna like a digital choir, while deeper electronics manage tracking, processing, and thermal stability. Beamforming is one of the most powerful tools in modern wireless communication. Instead of wasting energy in every direction, it concentrates signals exactly where they're needed, improving efficiency, boosting signal strength, and enabling long-distance links with relatively small, low-power antennas. Without it, Dishy would have to blast signals everywhere, wasting power and creating interference. With it, the beam becomes precise, targeted, and efficient. Now, this becomes even more interesting when we talk about beam steering. By adjusting the phase of each antenna element, the dish can tilt its wavefront and redirect the beam electronically. Unlike a mechanical dish that physically rotates, this system tracks satellites almost instantly, with no moving parts to wear out. In principle, phased arrays can even form multiple beams at once, a capability often used in advanced radar and military systems. For Starlink, a single main beam follows each satellite, but the underlying technology could scale to far more complex patterns. This is revolutionary because it eliminates slow, failure-prone motors. Instead, electronic steering operates nearly instantly and with microscopic precision. The idea was first developed for Cold War radar systems to track fast aircraft and missiles. Today it delivers broadband internet. Of course, it's not just the dish doing the work. Each satellite also carries phased array antennas, forming multiple beams to serve thousands of users at once. It's like a conductor leading dozens of choirs, each singing in perfect harmony, but directed toward different listeners on Earth. Without phased arrays, none of this would work. A fixed antenna would spray energy everywhere, resulting in weak signals, massive interference, and no way to track fast-moving satellites. And once the beam is formed, that's when your data rides on top of it. When you stream a video, the dish modulates radio waves using advanced schemes like 6/4 where each symbol carries multiple bits by varying both amplitude and phase. This packs a lot of data into each signal, but it also demands an extremely clean connection. That's why precise beamforming and error correction codes like LDPC are so critical. They make sure your movie doesn't freeze even when the signal takes a hit from noise or interference. The dish itself is about 1/2 meter across, and while larger apertures naturally focus energy more tightly, Starlink's phased array multiplies the effect by combining many small elements into a virtual, super antenna. On the satellite side, phased arrays do double duty, not just for user links, but also for ground stations and even laser crosslinks between satellites. These space-based optical links create a mesh network in orbit, reducing latency and sometimes even outperforming undersea fiber cables. Of course, the engineering challenges are enormous. Dishes can only steer within a limited field of view, grating lobes must be carefully suppressed, hundreds of amplifiers generate significant heat, Doppler shifts from orbital motion must be corrected in real time, and satellite handoffs have to happen seamlessly without users ever noticing. Yet, despite all this complexity, the result is remarkable. Latencies as low as 20 to 40 milliseconds, compared to 600 milliseconds or more for traditional geostationary satellites. And the bigger picture, Starlink is more than just an ISP. It's transforming connectivity at sea, in the air, in disaster zones, and in remote villages. The same phased array technology once reserved for Cold War radars is now mass-produced for homes, schools, and businesses worldwide. So the next time you see a flat white dish pointed skyward, remember, inside are hundreds of antennas, all working together like an orchestra, shaping invisible beams, tracking satellites at orbital speeds, and carrying gigabits of data across a global space-based network.